I hope you enjoyed learning about the history of dogs and the messed up people who sometimes do weird things. It's the spite part, yeah. I mean, you dog, but quit doing the. Yeah. How cool is the fox experiment, though? The idea that, like, no, we didn't breed patchy coats and floppy ears into them. That's just what happens when you breed for tameness, because adrenaline is this chemical that you're reducing when you breed for tameness. But the production of, and the more you learn about biochemistry, the more you find out that, like, all these chemicals are connected. So making adrenaline, either adrenaline is a precursor to melanin or vice versa. Like, to make adrenaline, you have to make melanin first or something like that, so that reducing adrenaline is going to reduce that pigment color. And it's just, he was the first one to see anything like that, and we're finding out a lot more works like that as well. Yeah.
So I know, like, humans get adrenaline like when they're rock climbing or like doing a sport. Is that why humans get like so red when they have like?
The redness has to do with increased blood flow. Sure. I mean, I think there's different reasons for that near the skin where you would see it, but definitely adrenaline increases the diameter of blood vessels and your blood flow and that stuff. Yeah.
Does that mean if you get like a dog with really floppy ears, like
I don't know. I have no idea if there's a correlation. I mean, we think about the ones that have the upright ears, German Shepherd, Husky, those guys. They do kind of seem less tame to me, but I don't know.
Yeah, but sometimes they're unnaturally, because like my dog is a German Shepherd and Rottweiler, and their ears are floppy.
Or does like the patchiest coat mean the tamest dog? I don't know.
So if like humans had more adrenaline, would that mean like different hair colors and stuff?
I don't know that either. These are all great questions.
Yeah.
Yeah. So, okay, how did you do with this? The idea that you count the differences. This is just this was your homework, right? Did you do okay? Okay, but you started it. All you're doing is counting differences, right? That's all this graph shows. It shows that if you look at it, it's the same protein that you see all the letters on. It's cytochrome C, and this is just how many amino acid differences there are per 100. So, for example, different orders of mammals, like rodents versus canines, have something like 5 to 10 differences per 100. That basically puts them at 100 million years ago since their common ancestor. So it's just a direct correlation of how different is your DNA, how long ago was your common ancestor. That's all you're doing on that homework. Don't overcomplicate it in your brain. It's just counting and then making that graph like that, except yours is more of a family tree type thing. Any questions about that? Okay. Into chapter 17, we'll be testing 16, 17 together. Basically, now we got to start to apply what you know about genetics to evolution. The term gene pool of any species, any population of any species, just means all the alleles for all the genes that all of the organisms have. And in any gene pool, any one allele you pick occurs at a specific, what we call allele frequency. So each of those frequencies is something you can measure and know, calculate. Brady, need a pen? Pencil, Jack? Too bad. So I think an example I gave before was rabbits. We can stick with that. Long hair, let's say long hair is dominant to short hair in rabbits. And let's say in a particular rabbit gene pool, we're looking at a 50% frequency of the big H and a 50% frequency of the little h. which means half of the total alleles are big H's and half of them are little h's. You know, you guys ask like better questions than my honors classes. Yeah.
We're creative.
Like that brain teaser yesterday, you got that, right? Yeah, none of my honors classes did. Just saying, I don't see the big head, but keep it up.
I just.
Hey, does this mean that half the rabbits are long haired and half are short haired?
No,
Why not?
because it switch.
I don't know the money's very large.
Technically, they could all be long haired, couldn't they? And it would still be half and half. If that were the case, what would all the genotypes be? They're all heterozygous. Exactly. They could all be big H, little h, and those frequencies would be like that. Now, in reality, probably not. In reality, it's probably, typically about a quarter of them are homozygous dominant, a quarter of them heterozygous. No, half of them heterozygous and a quarter of them recessive. But not always. It depends. We don't care. We don't care what they look like right now. We just care what's going on under the hood. It's 50-50, and what's going to happen if the climate changes? If the climate changes to become warmer, what do you expect to happen to those numbers?
More short.
So this 50% would go up. Yep, the little h 50% would go higher, and the big H would go lower. That's really the basic idea of kind of the genetic basis of evolution. That evolution under the hood is a change in those numbers. Natural selection is the environment acting on the actual phenotypes, the actual organisms, traits, but the evolution that happens, that is purely a change in the numbers as far as how many of each allele there are. That, by the way, is one of those things that shows up on state tests and ACT type stuff frequently. Fill in the blank. Natural selection acts on blank, where evolution is really a change in blank. That's how you fill in those blanks. What?
You said frequently, and I looked at it and this is each allele frequency. Laugh about it. I just looked at it.
We're using biology vocabulary, dude. Jokes on you. I win. Okay, so the real meat of today's lesson is identifying the 3 types of natural selection that we can measure in polygenic traits. Remember polygenic? Remember eye color? And how there's 2 different genes? There's like brown and not brown, but then there's green and blue. And that most genes have even more than that. I'm sorry, most traits have even more genes that affect them than that. And that most polygenic traits, like we did human height, with a polygenic trait, usually we see a bell curve, like that one. Bell curves are so common in real life that statisticians, people who study statistics, call it the normal distribution. So, what we can look at now, it's a pain in the butt to do genetics problems with polygenic traits and bell curves, but it's very easy to look at what evolution does to them. It's very easy to look at what, for example, natural selection can do to that curve. It can move it in different ways that are pretty typical. So I'm going to come up with the weirdest examples I can of the 3 types. How do you feel about aliens? Should we use aliens?
Yeah.
Okay, let's say the aliens get here finally, but that's not good news for humans. Because the aliens are angry and hungry for flesh. They can fly, They kind of look like little birds that can fly, but have like razor sharp scissor-like beaks. And they're going straight for humans. But here's the thing, they're kind of fragile and they don't like to get too close to the ground. So they will only get about 6 feet.
No.
Yeah. They'll only let themselves get within 6 feet of the ground. The rest of the time they're up hanging out in the clouds. But they'll come down to kill, but they'll only get 6 feet from the ground. Who's in trouble? On this curve, who's in trouble? Where is that on the curve?
Uh-oh.
Yeah, there it is. These guys are in trouble, right? What's going to happen to the curve?
It's gonna like move.
Which way? I love that you said it's going to move. Most people say, well, they're just going to get rid of that part of the curve. That's not what's going to happen. It's going to shift to
Well, the middle.
the left, to the shorter end, right? You're getting rid of all the tall people.
Left.
You're still going to have a bell curve, right? You're still going to have people. Those people are just going to start getting shorter. There's still going to be an average, and it's still going to be rare to have, exceptionally tall or short ones.
Oh, do it.
So this is called directional selection. The kind of selection that moves the curve one way or the other, right or left, is called directional selection. Critters at one end of the curve have a higher fitness, the other end have a lower fitness. The curve shifts in one direction or the other. The textbook example is finch beaks. A lot of real-time evolutionary study has been done on the Galapagos finches. It's really cool stuff, but I figured I'd give you a spicier example. In this case, it was the only food that was available that year was like really tough seed pods, and so only the birds with bigger beaks could crack the seed pods, and so beak size went up that year. They actually observed that. An adorable old couple named Peter and Rosemary Grant, who've been studying those finches forever. You'll watch a video about them. No, they just every year, like for 50 years, they've gone to Galapagos Island, catching birds, measuring their beaks, and like tagging them. And like they know these birds personally. It's really cool. No, he talks about like has, oh no, number 5306 died off that one. I like that one. Like very nice. There's people at birds.
Yeah.
They look like you. Okay, next. Let's move away from aliens toward babies. See? Yeah, babies are weird. Okay, what makes us human? What?
It's our what good and evil. It's our mind. It's psychology.
The M one. Mind. You said ability to reason, consciousness. Where is all that located? Yeah, it's our big fat brains pretty much that make us human, right? So here's a question, why aren't they bigger? If they're so great, why aren't brains bigger?
That's gotta be a defense thing.
It's not what you think. Chris?
Take a wild guess.
Yeah.
That humans are the size they need to be for their
I feel like we could use a bigger brain. There's a reason we don't have it. Landon.
Wouldn't it be because if you got too big of a brain, we wouldn't be able to stabilize it with our neck?
Yes, but then couldn't you just develop a bigger neck? I mean, I think you're right. I just feel like it could be, if this is an L, I think we could use an XL. There's a reason we don't have an XL. And it's a hard limit that you probably don't think about.
So we don't.
We couldn't put our shirts on.
Close.
Close.
It's close to you couldn't put your shirts on. It is about your head fitting through something.
Oh, no. Oh. You're not doing it.
Wait a minute. But we've even gotten around that hard limit of the size of the birth canal, as we call it, right? Because if it's too big, it doesn't make it out, and then mom and baby both don't make it, right? We got around that, not C-section. Before that, when humans evolved the ability to wait to set their skull bones until after you're born. Anybody who knows about babies knows about the soft spots, right?
Yeah.
That's just the plates in their skulls haven't welded together yet. And the reason they're like that is so the head can squish when it comes out. You had a bigger head when you were born than should have been able to fit through that birth canal, except for your ability to squish that head, which is why naturally born babies look like they've been boxing, been beat up, whereas like C-section, they look perfect because they haven't had to go through the Play-Doh fun factory of life. Make sense? So there's a limit on the high end of, if this is baby head size, you're not going to make it here. And then low birth weight is bad too, right? Low birth weight correlates with high infant mortality as well. So both ends of the curve are being selected against. What happens to the curve? It kind of squishes, like a baby's head. Yeah. That's stabilizing selection. And there's a baby on that graph. Yeah. Looking at you, Reagan.
Yeah.
Man, there's no way I can edit this video.
The whole thing. It's just broke.
I hope they're okay at home. I hope you're okay.
But they're more okay than we are. I was watching like the notes video or something because I was here. I heard Kate.
Yeah, his voice does come through.
I'm on TV.
So directional moves the curve one way or the other. Stabilizing kind of squishes it in a little bit. You should be drawing these, by the way. Like just the dotted line and the solid line, showing that it started out one way and then it moved to the other way. If you didn't draw directional, it was just it was just like this, and then that kind of thing. Okay, back to the aliens. How am I going to do this? Okay, so same aliens. They're razor sharp beaks. They like human flesh, but they will. Let's change the height to 5 feet, and they really only like it 5 feet from the ground. That's the only place they want to be. But the good news is they don't do so well with like hard parts. They really kind of need soft, squishy parts if they're going to get you.
Oh.
Yeah, so they're flying 5 feet above the ground. Is that about here?
Yeah.
They want soft, squishy parts. Who's in trouble?
Fine.
Me, for one, and anybody with a neck right about there. If you're taller than say, you know, a few inches taller than me, chest, bird bounces off. Maybe you get a cut, but you're fine. Right? If you're shorter than that, head or over your head, and you're fine. It's the middle people that are in trouble. With me? What does the curve do? Oh, Chris, good. Do it again with your finger. Watch Chris.
Oh.
Yep. It's called disruptive selection, where basically both ends of the curves have high fitness, middle has low fitness. And what's interesting about this one, this is really the most interesting one to evolutionary biologists, because what it can do is actually split a population into two distinct different phenotypes. Let's follow this one a little bit. Let's play make-believe a little longer. And let's say that's what happens, that basically because of these alien bloodthirsty birds, the human population now has two distinct subgroups, tall people and short people. There are no medium height people anymore. You've been around humans a fair amount. Could you see there maybe starting to be some tension between tall people and short people? Could you see maybe, I don't know, there being some, I guess you would probably call it racism. Oh, no, you can't date him, honey. He's a tall person. We don't, our family doesn't date tall people. Right? Could you see maybe the tall people and the short people not hanging out together, maybe living in separate places? Like tall, he's tall. You say tall lives matter. Yeah, well, here's the thing though. Here is the thing. If those two subgroups become different enough that they can't or even won't interbreed anymore, what do we have now?
Dwarves and giants.
Two different what? That's how we define species, isn't it? Species is critters that'll interbreed successfully. If they won't or can't, that's speciation. We've created two different species. That's interesting. So those are your three types. We got directional selection, moves the curve one direction or the other. Stabilizing selection kind of squishes it because you're selecting against both ends. Disruptive selection, you're selecting against the middle, you're moving the curve, giving it a little dip in the middle, but eventually it can become so dramatic that the curves completely separate. And at that point, if they're not interbreeding anymore, you've got speciation. Questions? I do have an activity that goes with this. I'm not going to give it to you because you have your molecular clock thing, and I want you to have a little bit of time here at the end to break that out and see if you can make sense of it. So please do that for the remainder of the time. Those molecular clock worksheets are due Monday.